Okay, so this is a summary of the main formula that we've obtained so far. The next thing I want to do exactly the same manipulation, but for phi dot. So we would have an integral d3p e to the I p dot x, and here we would have the time derivative phi dot of x. Now, you could actually go back to the expression that we wrote for phi dot above. So let me just remind you, you could go back to this expression over here, and you could carry out a very similar analysis to what we've carried out so far. But a much easier thing to do is just to differentiate with respect to t the formula that we've obtained. So if we do that, differentiating the first term, well, the time derivative will bring down minus I omega. So we'll be left with a minus I over 2 alpha p tilde. We'll have an e to the minus I omega p t. And then for the second term, the derivative with respect to time will bring down I omega. So we'll just have I over 2 alpha p dagger e to the I omega p t. And the good news is now we have got one equation for alpha p tilde and alpha p dagger, a second equation for alpha p tilde and alpha p dagger. So we can solve these two equations and get a formula for alpha p tilde and a formula for alpha p dagger. Now, notice something. So let's call this equation equation 1, and let's call the second equation equation 2. If I take, so I want to take omega p times by equation 1 minus I times by equation 2. Okay? So take a look at what will happen to these terms with the alpha p tilde. So from equation 1, the coefficient of the alpha p tilde will be the 1/2 of the exponential. And from equation 2, because we multiply by minus I, it'll be minus 1/2 in the exponential. So if I take that particular linear combination, it means alpha p tilde drops out, because what I get from equation 1 exactly cancels what I get from equation 2. So that's the logic. Let's just go ahead now and do it. Okay. So we're going to have an integral d3x e to the I p dot x. Then we've got omega p times equation 1. So this is omega p times by phi of x minus I times by equation 2, which is phi dot of x. Good. What is this equal to? Let's just write it all out. So omega p times equation 1 will give us 1/2 alpha p tilde e to the minus I omega pt. And then omega p times the second term will be plus 1/2 alpha p dagger e to the I omega pt. Then we've got minus I phi dot. So multiplying the minus I into equation 2, we've got minus 1/2 alpha p tilde e to the minus I omega pt. And then that second term, the minus I times the I will be a plus. So I'll get plus 1/2 alpha p dagger e to the I omega pt. And then exactly as I motivated for you, this term exactly cancels against that term. So all of the alpha p tildes are gone. And what we are left with is a 1/2 plus a 1/2 is 1. So this is just alpha p dagger e to the I omega p t. Okay, so now it is particularly easy to solve for alpha p dagger. Alpha p dagger is equal to, I'm going to take the exponential over to the other side, So minus I omega pt, we have an integral d3x e to the I p dot x. We have got omega p phi of x minus I phi dot of x. Very good. So we've now got a formula for alpha dagger in terms of phi and phi dot. Now you could go through the same exercise to get a formula for alpha. That would be, I think the correct term is witless, because you can get a formula for alpha p just by daggering. So if we dagger the equation that we've got, alpha p dagger becomes alpha p is equal to, the dagger will just complex conjugate the exponential, so we'll get e to the I omega pt, d3x is real, so nothing changes to the d3x. The sign in the exponent will change to a minus ip dot x, and then omega p is real, so nothing happens to that. Phi dagger is equal to phi, so nothing happens to phi. The complex conjugation changes the minus I into a plus I, and then again phi is Hermitian, so phi dot stays the same. So there is our formulas for alpha dagger and alpha. Now, I started off by telling you that these were extremely important formulas, and they are. I'm going to explain why in a minute. And then the second thing is, you know, they might look a little bit complicated to you and a little unfamiliar. Okay, so now let me put some intuition into these formulas. We've been studying the free field so far, and you know that the free field is all based on the harmonic oscillator. Now, we had quantities like this appearing in the harmonic oscillator. So if you've got alpha p dagger and alpha p, the natural thing that corresponds to alpha p dagger and alpha in the harmonic oscillator is a dagger and a. That's the natural identification to make. We also have phi and phi dot. And the natural identification to make is that phi is like the position x, and phi dot, so that would be something like x dot, that's like the momentum p. So this is how you should be translating between our field theory and the harmonic oscillator. And when we solved the harmonic oscillator, when we solved problems, one very important formula was the formula for A in terms of X and P, and the formula for A dagger in terms of X and P. And if you remember, A looked like omega times by X plus IP, and A dagger was omega times by X minus IP. But now take a look at these formulas. So A is omega X plus IP, alpha p is omega p phi plus I phi dot. So if you were to replace the x by phi, the p by phi dot, you're basically getting the second box formula. And exactly the same thing for A dagger. A dagger is omega x minus IP, and we get omega p phi minus I phi dot. So why are these formulas important? Well, you know how useful it is to be able to translate between A dagger and A and X and P in the harmonic oscillator. And then secondly, although these formulas look quite complicated, there's a very simple interpretation of them. You're just changing between creation and annihilation operators and, if you like, the position and momentum of the field. Good. So good luck with these exercises. I think that you're building up some muscles by doing all of these exercises. So work hard, and let's move on to the next chapter.